Okay. So, we have seen how to construct groups with one axis of rotation, okay, and various other reflections and other symmetry elements. We call these groups CNs, DNs, etc. And depending on the existence of other symmetry operations, we call them CNV or CND or CNH and so on, or DND and so on. Okay. Now, the distinctive feature of all the groups that we considered so far was that they had only one Cn axis where n was greater than 2. Okay. They could have had multiple C2 axes, but we never considered groups that had multiple Cn axes where n is greater than 2. Okay. So, now what we are going to consider is groups where there are multiple symmetry operations, okay, of multiple Cn axes where n is greater than 2. Okay. Now, this seems a fairly complicated topic, because you can imagine that if you have one C3 axis pointing in one direction, another pointing in another direction, and you can imagine that things might get very complicated. And you might also believe that there are many classes of such groups, but actually, if you work it out, you can show that there are only a few distinct cases of such of molecules with such symmetry. And so we want to look at molecules that have multiple Cn axes where n is greater than 2. Okay. Now, fortunately, these can be visualized quite easily. Suppose a molecule has multiple Cn axes where n is greater than 2. Okay. Then you can represent it by what are called these regular polyhedra. Okay. So, to give you an example, the example that you are familiar with is suppose you had a molecule that was tetrahedral. Okay. You can imagine that you have this regular tetrahedron. Okay. This is a pyramid, and let us assume that there is a molecule right to the center, and you have molecules at these vertices. Okay. Now such a molecule with such a shape will have the symmetry of this figure of this solid. Okay. And if it has the symmetry of this solid, then you can easily, by representing it in this solid form, you can easily see what are the various symmetry elements. Okay. So if you were to list the various symmetry operations for this solid, okay, you can just imagine that the molecule has the shape of the solid, and you can represent all the symmetry elements. So, let us take a molecule with tetrahedral shape. You can easily see because each vertex is an equilateral triangle. Okay, each vertex is an equilateral triangle. So, in this pyramid, each vertex is an equilateral triangle, or each face is an equilateral triangle. Each vertex looks identical. So, one vertex looks completely identical from the other. Okay. So, this is the feature, such a solid where each face is a regular polygon and each vertex is identical is called a platonic solid. Okay. And so the thing about this is now you can see that any axis, since there are four corners, any axis that passes through one and through the center of the other, through the center of the opposite face. So, it passes through one vertex and the center of the opposite face. So, an axis like this or like this passing from here and coming out on this side, such an axis will have a threefold symmetry. So, you can imagine if you look straight through an axis passing through this way and passing through this vertex, you can imagine rotating by 120 degrees, you will get back the same figure. Again, rotating by 120 degrees, you will get the same figure. Okay. So this is a threefold axis of symmetry. So, this is a C3 axis, but similarly I could also do the same thing for this face, and I could get another C3 axis, or I could do for this face, I could get another C3 axis, I could do it for this face, I could get another C3 axis. So, essentially this molecule with such a shape will have 4 C3 axes. Okay. Now, you can do this is a tetrahedral molecule, and you have seen many examples of these. Okay. You can also think, okay, so here I had a triangle, okay, and I had 3 triangles intersect at a point. Okay. Are there other possibilities? Are there other possibilities? Okay. And if you start working it out, you can either have 3 triangles intersect at each vertex, or you can have maybe 4, or you can have 5. Okay. If you have 4 triangles intersect at a vertex, then what you get, the object that you get having 4 triangles intersect at a vertex is called an octahedron. Okay. So, this is a regular octahedron. This is formed by attaching 4 equilateral triangles, okay, and they all meet at one vertex. So, this vertex, it has 4 equilateral triangles. Okay. Now, if you look at the octahedron, each vertex is identical. So, this vertex, every vertex has 4 equilateral triangles, and if you turn it around, you cannot tell which vertex is which. Okay. So, a molecule with this can have this sort of symmetry. For example, you can have a sulfur molecule at the center and 5 fluorines at these 6 vertices. Okay, so SF6 is an example of an octahedral molecule. You have seen many octahedral molecules in your inorganic chemistry courses. Now, what are the various axes? And here you can immediately see that any axis that passes through this vertex and the opposite vertex. So, that is if it comes in like this and comes out from this side, this is a 4-fold axis of rotation. Okay. And you can have 1, 2, 3. You can have 3 4-fold axes of rotation. Okay. Also, you can see that if you had an axis that comes, let us see, yeah. So, you have these 3 4-fold axis of rotations. You can also have other rotation symmetries that we will shortly see. Okay. What else can you have? So, here you had 4 regular triangles meeting at one vertex. Okay. Now, you can ask, can you have 5 triangles meeting at a vertex? Okay. So, if you had 5 triangles meeting at a vertex, then the object you get is called an icosahedron. Okay. So, this is an icosahedron. If you look at this vertex, there are 5 triangles that meet at this vertex. Okay. And then if you look at every vertex, it has 5 triangles meeting at it. So, every vertex is identical, it has 5 triangles meeting at it, and this is a very nice symmetric figure. Now, this object, this icosahedron, there are certain molecules that have icosahedral symmetry. The well known one is the fullerene molecule. The C60 molecule has an icosahedral symmetry. Okay. And there are other molecules also like B12H12, that is another molecule that has icosahedral symmetry. Now, you can look at this axis. You can look at an axis that passes through one vertex and through the opposite vertex. This axis is clearly a 5-fold axis of rotation. Okay. So, now there are a total of 5 plus 5, 10 plus 2, 12 vertices. So, there have to be 12 5-fold axis of rotation. So, there have to be 12 5-fold axis of rotation. Okay. So, 6 5-fold axis of rotation. So, passing through one vertex and the opposite vertex. So, there are 6 pairs of vertices, and each of these will be a 5-fold axis of rotation. So, if you look at it this way, now you rotate it by 120, you rotate it by 72 degrees, you will get back the same thing. You rotate again by 72, you will get the same thing. Again 72, it is a symmetry operation. So, all these are symmetry operations. Okay. So, an icosahedral is a figure that is made, it is made fully of triangles. Okay. And there are at each vertex there are 5 triangles. Okay. Now, you can immediately see that if you take your 3 objects, you take a tetrahedron, you take an octahedron, and you take an icosahedron, you can immediately see that this out here it was almost more sharp here, out here it was even sharper, but here it is getting more and more rounded. Okay. And what I want to emphasize is the following, that suppose you had 6 triangles meet at this vertex, okay, 6 equilateral triangles, then each equilateral triangle the angle is 60 degrees. So, if you had 6 of them meet, then they add up to 360 degrees. So, the only way that can happen is if it is a plane, if it meets in a plane. Okay. So, essentially you cannot have 6 triangles meet at one vertex and form a non-planar object. Okay. So, therefore, you can have at the most you can have is 5 triangles meet at a vertex. So, the only regular polyhedra that can be made using triangles are the tetrahedron, the octahedron and the icosahedron. Okay. So, you can have only 3 such solids, so 3 platonic solids made entirely using triangles. Okay. Next we can look at suppose instead of using triangles, I started using the next polygon, regular polygon, which is a square. So, if I use a square is a regular 4-sided polygon, okay, where all the angles are the same and all the vertices have the same length. Okay. So, if you have three squares meet at a vertex, then what you get is a cube, okay, because every vertex has three squares that meet at it. So, 1, 2, 3. This vertex has 1, 2, 3, and so on. So, every vertex has exactly 3 squares that meet at it, and the object that you get is a cube. Okay. So now a cube, you can immediately see that it has a C4 axis. It has this axis that passes through one vertex, and the opposite vertex will also be a C4 axis, and so on. Okay. Now, can you have 4 squares meet at a vertex? Okay. Can you have 4 such squares instead of 3 squares meeting at a vertex? 1, 2, 3. Can I have 4 squares meet at a vertex? And the answer is that if you have 4 squares meet at a vertex, then the figure will become planar, because each angle is 90 degrees. So, 90 into 4 is 360. So you cannot have 4 squares meet at a vertex. So, the cube is the only platonic solid or the regular polyhedra that can be made using squares. Okay. So, we saw that there are 3 regular polyhedra that can be made using triangles, but there is only one regular polyhedra that can be made using squares, and that is the cube. Okay. Next polyhedra, we can ask, okay. So we came to 3-sided polygons, which is a triangle. We used squares. Okay. Now, can we use a pentagon? Okay. The pentagon, and if you use a pentagon, now in a regular pentagon, each angle is 360 by 5, that is 72 degrees. So, each angle is 72 degrees. Okay. Now, if you had if you have a regular pentagon, each angle is not 72, but 108 degrees, 108 degrees. Each angle in a pentagon is 108 degrees. Okay. So, it is 540 by 5, that is 108. Okay. So, you have 108 degrees here. Okay. So, now you can ask how many pentagons can meet at a point, and to get a non-planar figure, and you can at the most have 3. You can at the most have 3 pentagons meet at this vertex, because if you have 4, the sum of angles will be 432, which is greater than 360. Okay. So, the only way you can have a regular polyhedra using pentagons is to have 3 pentagons meet at one vertex. Okay. And this figure involve having 3 pentagons meeting at a vertex is called a dodecahedron. Okay. So, this is called a dodecahedron. So, the whole figure is made using pentagons. Every vertex has 3 pentagons meeting at it. Okay. And it is made using many of these pentagons. Okay. Now, now there are interesting symmetries in a dodecahedron, but clearly you can see that if you take an axis that passes through one vertex and comes out through the other, okay, then it will have a 5-fold symmetry. It will have a 3-fold symmetry. Now, if you take an axis passing through the center of one pentagon and coming out through the center of the opposite pentagon, this will have a 5-fold symmetry. Okay. So, there will be a 5-fold rotation axis passing through this center and that center, and there will be a 3-fold rotation axis passing through this vertex and this vertex. Okay. So, It turns out now you cannot have a figure using hexagons, because the moment you put 3 hexagons, the sum of angles becomes 360 degrees. So these are all the possible platonic solids that you can have. Okay, so there are only 5 platonic solids, and these are regular solids that are made using regular polygons. Okay. Now these 5 platonic solids, why did we study these platonics? Why did we bring in these solids? Is because to understand the symmetry of a molecule that has tetrahedral geometry, okay, you just need to understand the symmetries of this of the tetrahedron. Okay, so if you know the symmetries of this solid object, okay, then you know the symmetry of a molecule that has this symmetry. Okay. Similarly, if you know the symmetries of this octahedron, you know the symmetries of a molecule that has octahedral geometry. Okay. So that's why we just need to understand the symmetries of these solid objects, and you know, making such models is a very useful thing, and you know, you should I encourage all of you to make such models. In fact, the act of making such models is quite instructive. You can also purchase them at various stores. There are you must have seen models like this which you use in your organic chemistry courses. There are very nice models that are available. This is a model that shows an ethane molecule. Okay, you must have seen, and this can be the staggered form. This is the eclipse form, and once you use such models, then you can understand the symmetries of these objects very well. Okay, so for example, this is an example of a molecule with octahedral symmetry. Yeah, so this is a molecule that has octahedral symmetry. Okay, now if I want to understand the various axes of rotation, I can just see that this is clearly a 4-fold axis of rotation. This is also a 4-fold axis of rotation. I can also imagine an axis that passes like this, so that would also be a 4-fold axis of rotation. Okay, so I encourage all of you to either you know, if you have access to such models, you can get them, or else you can make them using simple clay and matchsticks or things like that. Okay, so now let's thoroughly analyze the various symmetries of this tetrahedron. So what are the various operations that are present in a tetrahedral molecule? Okay, so that is our next task that we want to do, and you know, it's a fairly laborious task, but you can work it out. I have written the solution right here. So a tetrahedral has the identity. It has 8 C3s. Okay, and you can easily identify these 8 C3s. Okay, so you can easily identify that this is a C3 axis. This is a C3 axis. This is a C3 axis, and this is a C3 axis. So these 4 are relatively easy to identify, but there are also 4 more C3 axes in a regular tetrahedron, and these can also be identified. These correspond to axes that pass through the midpoint of one vertex. Okay, so you can imagine an axis that comes out passing this way. So clearly this is a 3-fold axis of rotation. Okay, so there are it turns out that there are not 4 but 8 C3 axes. Okay, so if you want, I can show this something like this, and you rotate it, you will get something like this, which is essentially the same geometry. Okay, so it has 8 C3, it has 3 C2 axes. Okay, so these are the 3 C2 axes. So if you imagine that you pass through the center of this vertex and through here, now this becomes a C2 axis, because you rotate by 180 degrees, you will get back the same thing. Okay, so you can imagine this way. So you come through here, now you rotate by 180 degrees, then it will come back to this, which is the identical figure. So these are the 3 C2 axes. The 6 S4, now each of these C2s corresponds to an S4. Okay, so each of these C2s, okay, so this axis that comes from outside through this point and comes out on the other side, This is a C2 axis because you can rotate by 180 degrees and you come back to the same thing, but it is also an S4 axis because you rotate by 90 degrees, you will end up here. Now you reflect it. If you reflect it, you will what will happen is this, you'll essentially see something like this, which is identical. Okay, so so that's the nature of this this 6S4, and then there are 6 sigma d planes. Okay, so so those correspond to these planes. So planes that that pass through any pair of atoms and bisect the opposite vertex. So they are the sigma d planes. Okay, so you have 8 C3s. Okay, and you have 6 sigma d. So that's the tetrahedral geometry. So I just want to come back to the tetrahedral, okay, and just make a connection. So you have 4 of these C3 axes. Each of them has 8 operations because they have each of them has 2 operations because you have C3 and C3 square. So that's how you get 8 C3. Okay, so you have 4 C3 axes. Each of them has C3 and C3 square. So you get 8 C3. Okay, and similarly you can work out all the remaining things. You have 3 C2 axes. Each of them is a S4 axis. S4 has 2 operations. So therefore you get 6 S4. Okay, so this in this notation when I write 8 C3, that means I have 4 C3 axes, 4 C3 operations plus 4 C3 square operations. Okay, so each C3 refers to, so therefore you get 8 C3s, C3 operations. Okay, so a molecule that has this symmetry, it's this set of operations forms a group that is called the tetrahedral group or the TD. It is denoted by TD. Okay, now let's look at the cube. Okay, let's look at the cube and the octahedron. Okay, now actually the cube and the octahedron, you know they have a lot of you can immediately look at the octahedron and you can say that I can put this octahedron inside a cube. Okay, I can inscribe the octahedron inside a cube. Just imagine, I think you can show this in this quite easily. So just I'll just do this. And okay, so here you have it. You have an octahedron that can be inscribed in a cube. Okay, and why is this relevant? Why is this so relevant? Why is it relevant that you can inscribe the octahedron in the cube? The answer is that the set of symmetry operations for an octahedron and the cube are exactly the same. Okay, I repeat, they are exactly the same. So an octahedron and a cube have exactly the same symmetry operations, and the reason is that you can have a continuous set of transformation from the octahedron to the cube. So you can imagine that you take the cube and you squish it like this, press it in a bit, okay, and ultimately you will end up with an octahedron with something that looks octahedral in shape. Okay, so this, the important lesson is that the cube and the octahedron have the same set of symmetry operations. Okay, so we'll see that by actually looking at the symmetry operations for both of these. So an octahedron, let's take an octahedron and we'll show that the cube also has the same symmetry operations. Octahedron has now each of, let's see, yes. So you see that this face looks like a triangle. So if you had an axis that passed through the center of this triangle, okay, and came out of the other side. So if you had an axis that came this way, okay, now that axis is a C3 axis. Okay, so you can do C3 rotations and you will get back the same molecule. Now the octahedron has a total of 8 faces, so it has 4 pairs. Okay, so it has 4 pairs of axes, and so there are 4 C3 axes. Okay, each C3 axis generates 2 operations, so there are 8 C3s. Okay, now you go to a cube and you ask, do you see exactly the same 8 C3s? And the answer is yes, it is very obvious that you see the 8 C3s. You just place the cube this way. Okay. Now, now imagine an axis that comes from there, enters through this vertex, comes out of the opposite vertex. Okay. So clearly, this axis that comes from there, passes through this vertex, comes out through the opposite vertex. If I rotate by 120 degrees, then this bond will go here. So you will end up with something like this, okay, and so on. So that is a C3 axis. And now since there are 8 vertices, there are 4 C3 axes, and 4 C3 axis means you have 8 C3s, 8 C3 operations. Okay. So, so we saw that both the cube and the octahedron have this 8 C3. What about the 6 C4? Okay. What about the 6 C4? And the 6 C4 are relatively easy to see. You in an octahedron, you just imagine that you pass through this vertex, come out of the other. That is a C4 axis. Okay, so that is a C4 axis. And you can see that there are three pairs. Okay, 3 pairs of C4 axis. Each of them has a C4 and a C4 cube. So there is C4, C4 square, C4 cube, and an identity. So you rotate 4 times. So you have 4 operations. Okay. Now, so you have 6. You have 3 into 4, 12 operations. Okay. Now 6 of them are we write them in this form. We write them as 6 C4 and 6 C2. Okay. 6 C4 and 6 C2. Okay. So C2 would correspond to rotating by 180 degrees. Okay. So start from here, rotate by 180 degrees. So you end up with something like this. Okay. So you have so each of these C4 axis is also a C2 axis. So you have 6 C2 axis. Then you have some other C2 axis also. So an octahedron, in addition to this, is also a C2 axis. Similarly, okay. Then an octahedron has an inversion symmetry, because if you imagine inverting this molecule, this will come here, this will come here, you will get identical molecule. So it has inversion symmetry. It has 3 sigma h. 3 sigma h can be thought of as the sigmas that don't contain the C4. So it's containing these. So this would be 1 sigma h in this plane. You can imagine 2 more planes like this and like this. Okay, so it has 3 sigma h, and then it has 6 sigma d. Now the sigma d planes would correspond to ones that pass like this. Okay, so you take any pair of atoms, okay, and you bisect them, and you will get a sigma d. Okay. Then the other interesting thing is that each of the C3s is also an S6. So the 8 C3s, they are also S6 axis. So the C3s, remember, you have to think of this triangle. So C3 is related to a triangle. So an axis that passes through this triangle was a C3 axis, because you rotate by 120 degrees, you will get back the same thing. Rotate again by 120, you will get the same thing. Okay. Now each of these is also an S6 axis, not an S3 axis. Okay. There is no C6 axis, but if you rotate by 60 degrees, you will end up with something like this, and then you reflect it, and you will end up back with the same figure. Okay, so we have all so each of these C3s is also an S6. Okay, each of the C2s is also an S4. Okay, so those are the various operations in an octahedron, and it's good to actually work these out gradually when you get started. I will show these axes for a cube also. So let's see, you can see the C3 axis in a cube. This is the C3 axis that passes through the opposite vertices. So clearly there are 4 C3 axes. Okay, so you get 8 C3. Each of these is also an S6 axis. So this is also easy to see. You imagine rotating not by 120 degrees, but by 60 degrees, and then you flip it. So and then you reflect it about this perpendicular plane. So that will end up with a molecule that had the same an equivalent configuration. Where are the 6 C2s? Okay, so what do the 6 C2s correspond to? And you can think of them as let's see. So each of these axis is also a C2 axis. okay, and each of, so you have 1, 2, 3 C2 axes, okay, but you can also have C2 axes that that pass through this way. So it passes through this and comes out of here. This is also a C2 axis, because I do a 180-degree rotation, you get back the same one. Okay. So there are 6 C2s. Similarly, the inversion for a cube is very obvious to see. The opposite corners get swapped. Then there the 3 sigma h are, you have 3 sigma h corresponding to this plane, and this plane. 6 sigma d's. The sigma d's are little more complicated to see, but you can see that one here, 2 here. Okay. Similarly, 3, 4 and 5, 6. Okay, and similarly for S4 and so on. Okay, so what we have shown is that the cube and the octahedron, they have the same set of symmetry elements, and they are essentially, as far as their symmetry group is the same, which is, and it is represented by OH for octahedron. Okay, you can similarly work out for an icosahedron, and the other, just as the cube and octahedron had the same symmetry operations, you can also show that the icosahedron and the dodecahedron have the same symmetry operations. Okay, this is slightly more difficult to see, but what you notice is that if you look at an icosahedron in this direction, you see a regular pentagon. Okay, which is the same object that appears in the dodecahedron. Okay, so by the same argument, you can put the icosahedron inside a dodecahedron. Okay, and such that each vertex will be at the center of the pentagon, and we can see that very quickly. So let's just put it inside. Okay, so I put the icosahedron, and notice now that each vertex of the icosahedron is at the center of the pentagon. Each vertex is at the center of a pentagon. Okay, so the icosahedron and the pentagon and the dodecahedron have the same symmetry. Okay, so now we can ask what are the various symmetry elements in an icosahedron or a dodecahedron, and it's not hard to show. We have to work them out. It's quite a long process, but if you work it out, you'll get that it has all these various symmetry elements. It has E, it has the C5s. So this is a C5 axis. Okay, so this is a C5 axis. Each C5 will generate 4 others. Okay, so you have C5 and C5 square. Okay, and basically, since there are 12 vertices in an icosahedron, there are 6 pairs. So you can have 6 C5s and 6 C5 squares. Okay, but each C5 will also generate a C5 cube, and each C5 square will generate a C5 4. So you have 12 C5s and 12 C5 squares, and then you have 20 C3s. C3s corresponds to axes that pass through one of the triangles, through the center of one of these triangles, come out from the triangle on the opposite side. And since there are 20 such triangles, there are 20. Oh no, sorry, there are 10. There are a total of, so if you see from here, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so 9, 10. Okay, so there are 10 such axes. There are 10 such C3 axes, and each of them will generate C3 and C3 square. Okay, so you have 20 C3. Each of these turn out to be an S6. Each of these 20 C3s turn out to be S6. Okay, and then there are some S10s and S10 cubes, and then there are 15 C2s. Okay, which can be understood as, see what's a good way. Yes, you imagine this. So you pass an axis through this vertex coming out of the opposite side. That's a C2 axis. Okay, 15 C2s, and then it has an inversion symmetry. Okay, so you can show that this icosahedron has the same symmetry as a dodecahedron, and this group has 120 operations, the icosahedral group. Similarly, the octahedron had 48 and the tetrahedron had 24. Okay, so these groups had both rotations and reflections. Okay, now you can see quite easily that if you take just the subgroup of rotations, okay, if you take a subgroup that includes only rotations, okay, then you'll also get a group okay, and these are the pure rotation groups. Okay, so the pure rotation groups, you can get pure rotation groups that do not have all these, that do not have all the reflections. Okay, and so if you had a tetrahedron, then the corresponding pure rotation group is denoted as T, and that has operations only E, just 4 C3s. Okay, so it just has 2 C3 axes. Okay, and it has 4 C3 square. Okay, so actually, and then it has 3 C2s. So it does not have the reflections, and since it doesn't have the reflections, it doesn't have S4 also. Okay, so it just has 4 C3, 4 C3 square, and 3 C2. Okay, so this is a subgroup of this group, and this is also, so there are certain molecules that have this symmetry, that is T. So you can imagine that you have the rotations. Okay, so you have all the rotations, but you don't have the reflection. So the molecule might have something that comes out in one direction here and another direction here. Okay, so this was a plane of reflection for a tetrahedron, but if you had something that pointed in one direction here and another direction here, then it would still satisfy rotation, but it won't be a reflection plane. Okay, so that was the that is this T, the group of pure rotations. Similarly, if you had an octahedron, you could have a group that involves only rotations in an octahedron, and so you have just the rotation operation. So you have the C4s, okay, and then you have the C2s, and you have the C3s. Okay, so you have C4s. C4 also gives C4 square, which is same as C2, and then you have the C3s, and you have this additional C2. Okay, so this group is denoted by O, and the tetrahedral group of the pure rotation group of tetrahedron is denoted by T. Okay, and similarly, you can have a pure rotation group of the icosahedron that is denoted by I. Okay, so it does not have the reflection symmetry. So there are icosahedral molecules that don't have reflection symmetry. Okay, and those are denoted by I. Okay. So are there other groups you can have that have multiple CN axes? Okay, and it turns out that there is one other group that you can construct. Okay, you can imagine that you have a tetrahedron, but in addition, okay, so the tetrahedron has these C2 axis. So this is an example of a C2 axis. So you rotate by 180 degrees, you will get back the same thing. So this axis that passes through here and through the center of this is a C2 axis. Okay, so the tetrahedron has a C2 axis, and now if this was a sigma h, okay, so the C2 axis in general is not a sigma h, but if it was also if you had additional sigma h planes, okay, then you would call this a TH. So it has a T and it has a sigma h. Okay, so it has T, it's not TD, but it has T and sigma h. Okay, so the number of operations for these groups, for this it is just 1 plus 4 5 plus 4 9, 9 plus 3 12. So this has only 12. Okay, this had 24. Okay, now this has this is also 24. Okay, so this also has 24, but it is slightly different. It's not, in fact this doesn't have the S. I mean so it has an S6 axis. So here you had C2 and S4 for a TD. Okay, but now you have C3 and S6. So you have 8 C3 and you have 8 S6. Okay, because of this, and you don't have sigma D, but you have sigma H. Okay, okay, so that would be, and also you have the inversion symmetry. Okay, so this group is called TH. Okay, and it is slightly different from, it has the same number of operations as TD, but it looks slightly different. Okay, so that's about what I want to say about about TH. Okay. So, so basically we have seen how starting with the platonic solids we can identify all the groups that have more than one CN axis where n is greater than 2. Okay. So these are the groups that have multiple CN axes for n greater than 2. Okay. Now next what we want to do is to get a systematic procedure for identifying the symmetry group of a molecule. Okay, so you identify various symmetry operations, then you should be able to classify them into the appropriate group. Okay.